So, hi everyone. I'm Kanal. I'm at University of Chicago. This is joint work with Rusbe and my advisor, Bill. Oh, thanks. So this talk will be about a complexity class called QMA, and a related one called QMA2. And these are kind of a complexity theorist's approach to study entanglement. Both of these are verification classes. They're trying to describe problems that can be verified with a quantum computer. But in the latter one, the verifier knows something about the entanglement structure of the quantum witness. So the talk is to discuss approaches to saying something about entanglement from the lens of complexity theory. So QMA is a verification class. It's looking at quantum computers a quantum machine that can verify something. So it's a decision problem where in the yes case, there's some quantum state, we call this a proof or a witness, where given to the verifier, it can accept with probability at least C. In the no case, no matter what quantum state is given to the verifier, it will only accept with probability at most S. And now I should say that these in general are families of problems for every input size, n. So C and S can be functions of n, just like the time is polynomial in n. Okay. So the yes and no cases are often called completeness and soundness. So think of this as like the most common quantum version of an NP type class. QMA2 is going to be very similar. It's also going to be a verification class. But instead, the yes and no cases are going to have proofs that are split down the middle. So in the yes case, we know that the quantum proof is unentangled across a bipartition. And we can assume the bipartition is directly down the middle. So in the yes case, there's some quantum proof that has a psi1 part and a psi2 part, where the verifier accepts it with at least C. And in the no case, the verifier will accept with at most S, no matter what psi1 tensor psi2 it's given. Okay. I should first say that every QMA problem is in QMA2. If it's in QMA, it's in QMA2. How can I see that? A QMA2 protocol could ignore the second half. It could just throw out psi2. So then everything that's in QMA can just look at the psi1 and then complete the protocol. But the question you might ask is how much bigger is psi2, or is QMA2, excuse me. How much bigger is QMA2? Is it a much more powerful class, or is it just exactly the same as QMA? Does this extra structure in the quantum proof give the verifier more information to solve more problems? So I'll say some things that we know about QMA and QMA2. First, there's this notion of promise gap amplification. So this C minus S parameter is known as the promise gap. And it turns out that as long as it's bigger than an inverse polynomial in n, it can be boosted to anything close to 1, very close to 1. For QMA, the approach, at least one approach, is very simple. You use what's called parallel repetition. So in this, you run the circuit many times. In the yes case, the probability of success, the success rate will concentrate around C, but in the no case, it will concentrate around S, and you'll be able to tell the difference. For QMA2, this doesn't work, but there's an important primitive called the product test that helps you do something similar. That you can run multiple protocols, but make sure that the unentanglement is preserved. And this is from Harrow and Montanaro. We might also try to upper bound these classes. How powerful are these classes? So the simplest upper bound is nexp. This is like np, but exponential time. How can every quantum verification class is in nexp? Because I can run the verifier, that's a quantum computer, in exponential time, and I can simulate the witness or proof with non-determinism. So all the interesting upper bounds are going to be smaller than nexp, somehow stronger. For QMA, we know stronger upper bounds. We know it's contained in p space by looking at a semi-definite program to find the best witness. And in fact, you can do better. It's in pp. But for QMA2, we actually don't know any other upper bounds better than nexp. And there have been many approaches, but nothing has worked. And I think recently, at least some people are wondering, maybe there's a reason we can't do better. Maybe this simple change in the complexity class actually makes QMA2 very powerful. So recently, a class called QMA Plus was introduced by Geronimo and Wu. Actually, there'll be a talk on this later this session. And QMA Plus is going to be also a verification class. It's going to be decision problems with a quantum verifier, where in the yes and in the no case, we're going to ask for extra structure. We're going to ask that the quantum proof has to have non-negative amplitudes. Now let's say we're in the computational basis. I'm saying that all of the amplitudes in the computational basis are real and at least 0. And in general, you can choose any basis you like as long as it's efficiently computable, and you send the basis as well. So this is kind of strange. We're asking for extra structure, both in the yes and the no case. And we can say the same thing for QMA2 plus. It's just QMA2, but again, we have non-negative amplitudes. So at first glance, it's not actually clear if the plus is giving you more power or taking away power. Why is that? So in the yes case, I'm asking for a more restrictive condition. The proof that's going to make the verifier accept with probability C has to now have this extra property of non-negative amplitudes. So it might shrink the power of the class. But by contrast, in the no case, there's a limited amount of states of quantum proofs that can be sent. So that might increase the power of the class. So which one wins? Does the plus add or reduce power? So one thing we could do is we could maybe just ask for the plus assumption only in the yes case. We'll say, okay, we only want this restriction in the yes case. So that should make it smaller. It should shrink the power. So it turns out a result from 10 years back actually answers this, although they weren't talking about plus non-negativity. They showed that this is equal to QMA or QMA2. So that means that the yes part doesn't actually reduce the power of the class at all, so the no part must be increasing the power. So these plus classes are at least as big as the non-plus classes. QMA plus contains QMA, QMA2 plus contains QMA2. And the intuition here is that the fact that we're reducing the amount of cheating that can happen in the no case is what's giving you a lot more power, possibly a lot more power. So we can also talk about what we know about this QMA plus and QMA2 plus. So we could try gap amplification. Do the C and S parameters matter? And it turns out that the simple trick you might try of parallel repetition doesn't work. So why doesn't it work? If you try to run the circuit many times, you'll actually destroy the plus promise. So in the beginning, we have non-negative amplitudes, and we might try running the circuit many times. But after we run the first circuit and do some measurements, it's not clear that the remaining quantum state has non-negativity, has non-negative amplitudes. We might reintroduce complex phases into the remaining state. So this doesn't mean that gap amplification doesn't exist. It just means that this approach won't work. We could also talk about upper bounds, Maybe there's some way to upper bound these plus classes, at least QMA plus. But it turns out that semi-definite programs, which I think are the easiest tool to start with for these quantum verification classes, also don't work. And because if you try to write down a semi-definite program for this non-negativity constraint, it turns out this was already studied in the classical literature under the name copositive programming. And copositive programming, at least at polynomial size, allows you to compute independence numbers of graphs and other NP-hard objects. So this upper bound only will just give you nexp again. So you might say, okay, maybe the plus is actually really powerful. It's really confusing and strange. But I'll tell you that all quantum states are actually pretty close to a plus state. They have a quarter overlap with some plus state. How can you see that? Take a quantum state, split its real and imaginary parts. Take the bigger one. Suppose it's real. Now for the state, take its positive and negative parts. Take the bigger one. Suppose it's positive. That state up to a very small transform has non-negative amplitudes. In particular, it has no relative phase, but it has a quarter overlap with psi. So this implies that there are constants for large enough promise gap for QMA plus where it's actually equal to QMA. And the same is true for QMA 2 plus and QMA 2. So maybe the plus isn't actually that much more powerful. And so the origin, at least for our work, is a result of Geronimo and Wu's, which says there are other constants, if you make the promise gap small enough, but still constant, QMA 2 plus equals nexp. And this is a little bit surprising, like on the one hand it's QMA 2, on the other hand it's nexp. If there was a way to amplify the promise gap, it would mean those two classes are equal. And it would give you a resolution to why this QMA 2 class has been so slippery. Maybe it's actually very powerful. However, our work complicates things. And our main result is that the same thing works for QMA plus. So there are some small constants, CNS, some constants with a small gap, where QMA plus is equal to nexp. So now QMA is, I'll go on record, QMA is definitely not equal to nexp. QMA is inside exponent exp, so you'd have to have exp equals nx for those two things to be equal. So that means that, assuming this very weak thing, like QMA is not nexp, it's like saying P is not NP or something, there's no promise gap amplification for QMA plus. So how can you interpret these results? Maybe you can say, actually, that the plus is actually really powerful. It's not the 2, maybe it's like the plus is giving you some super weird power. But you might also be more optimistic about this line of research, and you can say, I do think QMA 2 plus has gap amplification, and that might help understand QMA 2 equals nexp. We might be able to still study these classes. But our work complicates things because it means whatever amplification trick you use is not going to work for QMA plus. It has to use the separability condition of the quantum proofs. Okay. So I'll talk briefly about some key ideas in the proof. From time, I won't go into the proof, and I have a longer talk online if you're interested. So first, we're going to put NP in QMA plus with logarithmic size proofs, log n size qubit, log n qubit quantum proofs. So what will we do? We'll start with an NP hard problem, a constraint satisfaction problem, and we'll appeal to the PCP theorem to say that this constraint satisfaction problem has a constant size gap. Then we're going to crucially use this plus condition, this non-negative amplitude condition. And the verifier is going to use this to make sure the quantum proof is of a certain rigid form. How can the verifier do that? the verifier will run some tests, which I'll give some intuition for in the next slide. If you pass the test, that means you're of the rigid form. And if you don't pass the test, the verifier rejects. In the yes case, the quantum proof can be of this rigid form. But in the no case, there's no way kind of to get around this rigidity. Once we have this rigid quantum proof, the verifier will check, the constraints of the satisfaction problem, the CSP. We'll just check a few constraints, and again, appealing to PCPs, we can get a promise gap, constant size promise gap. Now, all of this will scale to NX inside QMA+. And the only things we have to be careful about are succinct representations of exponentially sized objects. So the whole argument is really you can study at the log size scale with NP, and then everything boosts up the way you want. Now, the key idea, I think, behind this is, to me, about interference. It's like a personal opinion is, what is the non-negativity doing? And I think non-negative amplitudes are kind of making a quantum state sort of quasi-classical. And here I have two signals. On the left, they add up to 0. They destructively interfere. And on the right, they're non-negative amplitude signals, but they can't destructively interfere. And so somehow, if you knew that the signals had non-negative amplitudes, then you can say more about the quantum states. You can force certain conditions. In particular, the overlap with the uniform superposition is proportional to the 1 norm. So you can actually get weird other metrics from the quantum state if you knew that there were non-negative amplitudes. So the verifier will use this projector to the uniform superposition to get variable value pairs, or at least constraint value pairs, and force uniform superpositions of the answers to the CSP. Okay, so the conclusions here are that I think these promise symmetric classes, where we're modifying QMA both in the yes and the no case, they might actually be really powerful. But the promise gap can actually make a big difference. And so here we have a class that interpolates from QMA to NX, just in constants. And so here, one thing might be interesting is there maybe some phase transition? Is there something sharp going on that at some magic number, the power is QMA, and some other magic number, it's super powerful? But I think coming back to QMA2, I think the plus strategy of trying to study QMA2 using the plus classes is still viable, but it has a significant roadblock now. Because suppose you want to use this QMA2 plus and show gap amplification to prove that QMA2 equals NX. But then it has to use the 2 part, has to use the unentanglement, because it can't work for QMA plus. Any gap amplification strategy for QMA2 plus cannot work for QMA plus. And so these techniques might be a lot more difficult to find. They might not be impossible, but they're going to be harder. So I think that the core question is, what does this QMA2 plus have that QMA plus doesn't? So thanks.
All right, thanks Kunal for the really nice talk. Are there any questions? Please step up to the mic.
Thanks for a nice talk. Okay. Actually, I have to because you mentioned that there is an easy regime for this QMA plus, which the ratio C over S is greater than 4. I'm wondering, could you say a bit more about the hard regime, which is the NESPA hard part? Is there some threshold about the ratio, or just for some particular C and S is NESPA hard?
Yeah. So in our construction, we use some PCPs with the properties that we need, and actually, it's inspired by the PCPs from Geronimo and Wu. Mm-hmm. But we don't work out the exact constants. We just know that they are constant.
Okay, so just there exists some constant in the regime which is not known to be easy, and they are hard.
Yeah. Like C and S probably are off by C minus S is probably right now 10 to the minus 10 or something.
Okay.
Yeah.
I see. Thank you.
So my question is also about the slide. So is it possible that there's not a phase transition, like the way things are defined? Like how can it go smoothly between them? And then a related question: if there is a phase transition, can one study sort of its properties, like I don't know, critical exponents or sort of first, second order questions?
Yeah, I think this is a good question. I'll start with the first. Like, it might be that like the number 2 is just like if the gap is any number above 2, even 2 plus inverse poly n, then it's easy, and 2 minus inverse poly n, it's hard. But I don't know how to interpolate across the middle. And also, there could be multiple jumps. That's for sure. It could, like, for example, it could saturate at p space first or x, and then it's not clear at all. It's a good question.
Have you looked at how this extends to the more general case of QMAK? So for k bigger than or equal to 2?
Yeah, I think it's using the same techniques from Harrow and Montanaro. QMA k, where k is bigger than 2, is equal to QMA 2. And that approach also works for the plus.
Okay, thank you.
Other questions? Please, step up to the mic.
What about QMA n?
QMA. Yeah. So I think that was similar to the question. K can be an QMA 2, QMA 3, QMA k, where k is polynomial and n is the same as QMA 2, and that's really it's really surprising, yeah, to me.
Any last questions? Okay, if not, let's thank Kunal again.